Ranger 2, prepare to detach.
What? No! No! Cooper!
3.
Cooper, what are you doing?
Newton's third law. You gotta leave something behind.
Hello, Zia. It's nothing like a question in the middle of the night just before your exam. Thanks for that. Okay, so this is AQA AS Physics Paper 2, May 2024. So let's have a look. So question 1 is what you're asking about. So hacksaw blade, thin flexible mesh strip of metal. Figure 1 shows a blade clamped between 2 blocks above a horizontal bench. Pen is attached to the free end of the blade. Okay, so it looks like they're going to try and wobble this. Free end of the blade is displaced and released. So yeah, so you've got some sort of oscillatory motion. Time for each oscillation is t. You never measure the time for one oscillation because a huge random error in the reaction timing. So you do it over 20 oscillations maybe, and then divide by 20 to work out a mean. That increases or that reduces the percentage uncertainty in t. But let's have a look what they did. So they did 60, which is good. Okay, so the table shows measurements to 60t. Show that t is about 0.42. So the best thing to do is work out the mean T60. So your basic averages. So that's 25.20 plus 25.05 plus 24.97 plus 25.10, and then just divide that by 4. It says show that, so you've got to show it. And then once you've got that, so let me just work that out. So that gives you a mean of 25.08. Let's get rid of these things here. Okay, so then how do you work out t? You just simply do 25.08 over 60 oscillations. So divide by 60. So that gives me 0.418, which is 0.42. So the same decimal places as those. Right, so that's nice and easy. Only one mark, but if you don't show it, show that, then I don't know if they're going to give it to you. But be thorough. So figure 3 shows a trolley placed on a ramp that is inclined at a small angle. So basically this trolley is going to move down here, and this is going to end up scribbling on the, looks like a piece of graph paper here. So bit of a classic SHM practical from year 13, just to show SHM or the sine wave that you would get. Blade and pen are positioned such so that the tip of the pen rests on the graph paper. Dash line shows the rest position of the pen. Okay, so the dash line is, if you didn't oscillate it, it would follow this line here. Okay, but obviously we did oscillate it. So the free end of the blade is displaced as shown in figure 4a. The blade and the trolley are then both released at the same time. So yeah, you're going to get this squiggly line. Okay, so right, okay, then let's see what we're going to do. Right, so figure 5 shows the graph paper. Point P, let me just zoom out. Point P and Q mark the start and end of the continuous line drawn by the pen after trolley is released. Okay, so if it didn't wobble, if it didn't oscillate, this distance here, this dotted line, is the distance it would have traveled in a straight line. Okay, and yeah, because it's right. Okay, so TPQ is the time for the pen to draw the line from P to Q. S is the displacement of the trolley during TPQ. So if you can work out S and if you can work out T, you could probably work out the velocity at the end. And obviously U is 0. Okay, so it started from rest. So determine TPQ. Assume that time for each full oscillation of the blade is 0.42. So what we've got to do here is work out how many oscillations. So there's, if you look, so there's your start position, 1 oscillation, 2 oscillations. And then if you look, you've got, there's another half oscillation plus that bit there. So you've got 2 3/4, 2.75 cycles, or 2.75 wavelengths, if you want to look at that, because that would have been the third one, wouldn't it? So 2.75 so you got 2.75 cycles or oscillations, and then each one is 0.52, so you times by 0.42. When I put that in my calculator, I get 1.155 or 1.16 seconds. All right, so I've got the time taken. Now determine S, the scale of the graph paper is shown. Okay, so what you got to do, it tells you here, Each box is 20 millimeters. So how many boxes? 1, 2, 3, 4, 5, 6, 7, 8.5 boxes. Okay, so if each box is 20, so now does it want it in meters? Probably best put in meters. So it's 8.5 boxes times 20 millimeters. Okay, so that gives you 170 millimeters, which is equal to it does want it in meters here, 0.17 meters. Okay, so let's move on to the next bit. So determine the acceleration of the trolley. So what have you got? You've got S is 0.17 meters. You've got U is 0. Did they say we can ignore air resistance and friction? I think we can. Oscillate with uniform. There you go. With uniform acceleration, that means we can use SUVATs. Okay, so what do we know? Okay, so we've got the time taken. So T is, I just scrolled up, 1.16 seconds. And so we've got to work out A. Okay, so because it's at constant acceleration, so S is ut plus a half at squared. Ut disappears. We want A, so 2S over t squared is equal to A. So put your numbers in. So 2 times 0.17 over 1.16 squared. So put it all in. So I get about 0.25. Okay. So just be careful. Don't use your rounded answers. I think I may have, but I might have got away with it. So teacher suggests that the absolute uncertainty in S is plus or minus 2 millimeters. Now, what you got to do, you got to look at, well, what's the resolution of this paper? It looks like each box is 2 millimeters. So the resolution is 2 millimeters. So therefore, the uncertainty is plus or minus half the resolution. So that's your standard. So that should be 1 millimeters. But you've measured at the top here and you've measured here. So there's two measurements on the graph paper. So there's two measurements on the graph paper. So that means it's 2 times the uncertainty. So therefore, because obviously we made two measurements, two uncertainties have contributed to your value of S. So therefore it's 2 millimeters. So now percentage uncertainty in TPQ, or your T is 0.46, determine the percentage uncertainty in A. So A was 2S over T squared. So you've used S. So the percentage uncertainty in A is the percentage uncertainty in S plus T squared. So you use T twice. So it's 2 times the percentage uncertainty in T. Okay, so they're giving you that one. So that one is just 2 times 0.46. Okay, and this one you're going to have to work out. Now, the percentage uncertainty in S, so how do you work out percentage uncertainty? It's equal to the uncertainty over the value. Okay, so we've got all this. So it's 2 millimeters over, and it's over 170. And obviously you want it as a percentage, so you times by 100. So when I put all this in, so that is 1.176%. I'll just leave it plus 0.92%. Let me just scroll up. So we just have to work it out. So that gives me on my calculator 2.096 or 2.1%. Okay, so a bit of everything in that question. Okay, so the figure 6 is a diagram drawn by a student to explain why the trolley accelerates. The diagram is incomplete because the student has ignored the frictional forces. So using figure 6, it can be shown that G is A sine theta. Or how did they get to that? Don't forget, you've got that's theta, so mg sine theta. is your resultant force, isn't it? So mg sine theta, your resultant force, is equal to ma. A's cancel, so A is equal to g sine theta. Okay, so you may have come across that before. So let's have a look at what the question's asking. So what they've done, they've said the resultant force is mg sine theta only, which is then equal to ma. But if there is, what they've said here is incomplete because it's ignored friction. So with friction, the resultant force down the slope decreases because now, oops, sorry, can't spell, because the resultant force is now mg sine theta minus f. Okay, and because of that, the acceleration is now going to be less than, wrong way around, is going to be less than 9.81. Okay, so that hopefully sums up this 12 marker. Go to bed, Ziad.